about a bit of detection of synthetic content. And so far, we have been very much focused on in the first day, we looked at discriminative models to differentiate between classes. And then we moved on to generate the content ourselves, which means that now we have a ton of synthetic content. But in some cases, we need to detect them, right? So we can't just allow the synthetic content to be used. And in the cases, for instance, when you're applying for let's say for a passport, manipulate your photo and then you're uploading the manipulated photo, you want to be, right? And then comes also the other applications such as, let's assume that you have a face image, and it's very common in many of the countries to beautify the face image, right, before giving it to the passport. And a passport is typically valid for 10 years. In the span of 10 years, the face appearance would change. And if you already have changed the appearance in the first photo, that would impact a lot of verification pipeline, right? So then it becomes very important to detect that synthetically altered content. And then is the other motivation, for instance, in medical insurance cases. So if you are a medical insurance company, you are going to process each and every single claim based on the data that is provided to you, and this would sometimes include an X-ray image of fractured leg. Right now, if I really don't have a fracture, but I just want to get the money from the insurance, I could always go back and edit the photo so that it appears new, and then I can submit it to the insurance company. Right. So it's good for the consumer, but it's bad for the business. So in many of these contexts, although synthetic creation is very interesting, it could also lead to a lot of implications, and we are also interested in coming up with methods that can actually detect them, right? So it's a very wide topic, so I can't cover all the topics here, but at the very top level, what I'm going to cover is that I'm going to cover there is the synthetic content, and the synthetic content can be coming because of alterations, manipulations, or it can be from the creation itself. And within the creation, I'll talk a bit about a number of examples on deepfakes, and then I'll give one example on a couple of examples on compression detection, and I'll motivate them why we need to do that. Okay, I think most of you have already seen this example, right? So it's a deepfake of a particular person and it's being reenacted and the voice has been injected. So the person on the left is the original one, on the person on the right side is deepfake. And now you see that there is subtle changes in the face, in the speech, and so on. If I did not show you the image on the left side, sorry, on the right side, you probably would not be able to distinguish between these two images. And the quality of the image is becoming better and better every single day, which means we are faced with the challenge of detecting them to secure all the systems that we are using. So this is part one, which we'll talk in detail in tomorrow's session, two different kind of attacks. But just to motivate you why we should be worried about them. So if I'm just taking a face recognition system, yesterday we discussed and derived on how to come to this AUC metrics, ROC metrics, and so on. So here you can see that there are a number of systems that are being evaluated, and every single system that is evaluated, if the baseline was here, very close to the ideal performance, you see if it is a generated image, let's say somewhere here, all of these are coming very close to that, right? And not necessarily all of them are synthetic data, but some kind of editing has been happening, but still you are able to get very good accuracy, right? So which means that the systems will be under attack. So for instance, in this case here, if you look at the generic face swapping, you see the accuracy was 98%, and then here this case is 64%, which means we are still left, we are still have 36% error, which has accepted the deepfake images, right? So it has a bigger implication. So this is motivating from the deepfake itself, and this can be generalized for other kind of content. And I'm taking deepfake because deepfake is also used and generated using gun networks, which is one of the popular approaches. And these days you also have the same approaches generated using same deepfake generated using diffusion networks. Okay, so if I have motivated you enough, then I can also show you that if you look at the databases, so there are wide variety of manipulation, wide variety of synthetic content. The very first database is TIMIT, which is called deepfake manipulation. In the second case, it's CGI manipulation. For those of you who are coming from previous generation, you remember we used to have this computer graphics based manipulations, something similar to Photoshop. and that is the second generation there. And then you have the other one, which is deepfake gone, which is out here, which is here. And then you have a combination of this, and then the combination of other approaches which are non-learned approaches as well. So all of them lead to some synthetic content, right? So this synthetic content, if you look at the quality itself, you can see all the way from 64 cross 64 to 1080p. Some of them even going to 2060p, which is 2 megapixel images, right? Okay, and then you see also some examples here. You see the pristine images which are not manipulated, not deepfake, real images, and then the images that are on the right side are all the deepfake images, different family of manipulations. So what can we do immediately? As soon as we notice that there are some synthetic content, any synthetic content that I showed you yesterday, for instance, with the style GAN, we saw some artifacts on the corners of the images, right? So in these cases, they are not very obvious, but you can also see some clues. For instance, if you look at the first image here, if you look very closely, if I zoom it into this, now you start seeing that the appearance of the eye is not very realistic, right? So we typically don't have such kind of eye. Let's go to the next frame here. You see here, it's completely unrealistic. And then what about the nose? So you see some subtle changes here. We don't have double nostrils, right? In many common cases. And then if I look at the mouth region, there is an inconsistency here compared to the real image here, right? So here I see both the upper teeth and the lower teeth, and here it looks a perfectly aligned teeth of like a very well created model, right? So these are some of the models that we are considering. These are some of the clues. Then as soon as we have this, so now we can start thinking of creating some detection approaches. And now I'm going to give not specific about the approaches, but I'm going to give you an idea of how we can create this detection. And then it can be adapted to your own use cases. Maybe you are working on health images, medical images, or you're working on something else, or entertainment industry. In all these cases, you can apply these concepts, right? So the very first approach that came in this direction, or not very first approach, but let's say the first generation approaches, was looking at the blink patterns. So if I have a video, then I can start looking at how the eye is getting blinked, and then as soon as I have that, I can plug in any kind of feature detection, and this feature detection can be very simple LBP like features, binarized statistical information independent features, or now I have the tool of having deep networks, so I can plug in the deep network that is up here, right? You have a CNN network, and then you extract the CNN network, and now since we are talking about the video, it's signals at particular instance. So which means now I can go from 2D signals to 1D signal by plugging in LSTM, and then on each of this frame I can make a detection, addition, or I can combine all these additions together and then come up with a final answer. Okay, so now I give you one set of one family where I'm actually generating the content using the generative methods, but I'm detecting them using the discriminative methods. All right, and then this is very nice approach, but what happens in these days is that the deepfakes have become very strong, right? So these obvious artifacts of closing eyes is not valid anymore, because every single frame can go through this quality assessment, like using the measures like FID, LPIPs, and so on. You can make sure that the image is very high quality. That means this method would start failing. So what do we do after this? Maybe then there is this other method, right? Which is combining some of the concepts of
Deepfake is doing is it is simulating the blinking.
in the case of the deepfake is actually
trying to say if it is not blinking, then it is not a.
It's not a deepfake.
So now then deepfake has simulated blinking also to fool.
Yes, very realistic blinking. So now it's difficult for using the same approach, right? This approach will start failing. So what can we do now? So we can look at the classical machine learning, classical computer vision. So in the classical computer vision, what we do is we typically look at the landmarks, all the points in the face, And then these landmark points have to move in a certain way, right? So they can't abruptly change. So now if I have this knowledge, then what I can do is I can start modeling them, right? So I see that every single time the landmark has shifted from, let's say from, in this case, the landmark has shifted from A to B here. That means that there is something weird with the image. And an advantage here is that it also can make use of classical machine learning. So just by looking at the delta differences between 2 points, I can learn a classifier. If you don't want the classifier, you can learn a sophisticated deep learning classifier, and then you can say this is a deepfake or this is not a deepfake. Now I'm taking the example of deepfake, but it can also be applied for synthetic data, right? And then if you look at this particular case here, now you see that the detection performance is now quite high or relatively high. But then there is a problem. The problem is that not in all settings we can get such high quality data, right? So in the wild, when I'm trying to look at the images that is captured from a surveillance camera, if I were to say that if it's a deepfake or not a deepfake, then I'm going to start failing with this approach. So what can I do now? So I can extend this a bit further. I can say that, okay, if not only by looking at the shift in the landmarks, but then I'll also add some kind of blur, some kind of noise into the data so that my method can become better. So there was one other work which was done in a similar direction, where they first take the landmark, and once the landmark is detected, they do a affine transformation, which is nothing but any edge that is tilted, you are correcting it back to the right position, right? Once you have the right position, now you can do your processing. And at this point of time, you can start using your CNNs, start plugging in any CNN, and then you extract the features and then try to see if it is detecting it or not. And again, remember that I'm going to introduce a wide variety, a family of approaches here. So just take the buzzwords for the lecture today, and then you can try to think which kind of approach can be used in your own research work. Okay, and then the advantage of this one, or at least this work which was published in 2018, is that there was no binding with what kind of CNN networks you should use. So which also gives me the flexibility of using vision transformers that we discussed recently, right? So it's a plug and play, mix and match system here. And then some of the researchers, they also started looking very closely into the mouth region, right? So they started seeing that synthetic content, whatever is generated using diffusion, whatever is generated using GAN, they will have very unrealistic mouth region, which if I have this background knowledge, then I can simply design a method which is looking only at that features, right? Now, all the approaches that we discussed so far, we can plug into this, right? Put a CNN, put a SVM classifier, or extract the features and then learn your own classifier, MLP based classifier, and so on, and then you can create your own classifier. Okay, and then there is this GAN family, at least the first generation GAN family. They are known to generate some kind of artifacts which are typically color aberrations. So what do I mean by color aberration? So if I start looking at this particular frame, and then I just slice one region, one particular pixel here, and then I start plotting them across different frames, I start noticing a pattern. You see a signature there on the top part here. So the color is changing in this area. So across all different frames, right? So the moment I know that, now I can say that this is a signature, right? It becomes a signature. Now if I learn a classifier to identify that pattern, then my detector becomes much more robust. It's an idea? Yeah. So now again, the assumption here is that this works on video. Second thing, that the color reproduction is consistent. But what happens in real life? Not everything is reproducing the color perfectly, and you have always noise in the camera, in the capturing environment, in the lighting condition, which means that these methods will start failing in such instances. Right? But if you just take the same example And then, or if you take the same principle of using the color based approach, you can start looking at how much is the color varying across different images. So here there are two different approaches. One is program based approach, which was discussed yesterday, and then we have the second approach, which is called glow based approach. Both of them are creating the images. And now if you are trying to convert the image from RGB color space, RGB is your typical image that you see in your smartphones, right? So it has three channels. Now this three channel image can be transformed to another color space, which is used in media production, which is used in television transmission. So there are different kind of color spaces. So the moment you you transpose the color space from one domain to another domain, and you can start measuring the difference between the color reproduction. So here you can see that whenever you are able to localize such color changes, it will also point you to where exactly was the manipulation that was happening, right? And now for those of you who do not like classical machine learning, by looking at this color space, taking the absolute differences, what you can do is you can go a bit further and then you can start learning your own networks. So in this case, what I'm going to do is that I'm taking the image in the RGB channel, which is on top left here. Then I'm going to convert it to a color space, which is called hue, saturation, and value, or YCBCR, whatever is your favorite. And then each of this channel will show you different information. If you look at this one now, if you see that in the S space, it almost looks like a photo negative, right? The old style cameras that we used to use. So that is the important information that is capturing. And then the two other components, they will also capture some complementary information, which is not visible in RGB naked image. So as soon as I have that one, then I can start coming up with an approach which finds the residual between the original image and the reconstructed image. Now, the concept that we learned about the variational autoencoders, we can easily plug it in here, right? So if I have an image, and then I try to reconstruct the image back using the variational autoencoder, I should get an image exactly like this. If there is a difference, that means that it has not reconstructed the image properly, right? So now we can see the bigger picture. So we are connecting all the things that we have been learning. And then as soon as I have this, I could simply go to a very simple approach of creating a histogram of all the differences and then plug in any kind of classifier that you want. You want an SVM classifier, you want a KDA classifier, if you want a deep learning based classifier, you can plug anything there. Okay, I'll not talk about this performance improvements and so on. You can look into the slides and then you can find all the performance improvement. But I just want to introduce you to all the family of detection approaches. And now is the other one, right? So this is also a very interesting approach. Those of you who have used digital cameras, you all know that whenever you take a picture, there is a particular signature inside that. People working on watermarking, you would have noticed this one. But if you have not worked on watermarking, nothing crisis. But if you look at this image here, for instance, this one, right? So every time you're taking a picture from a particular camera, the real camera, there is a fingerprint that appears inside the camera sensor. And that fingerprint is very unique, which means my camera will give me a different fingerprint compared to Professor Nain's camera, right? So if I have that knowledge, then I can model all the cameras in the world approximately, and then I can say that anything that is not following this laws of physics is synthetic content.
Actually, it is used in printer technology. Every printer you use, there
Yes.
is a universal code. There is a black dot,
Exactly.
very fine dot. It's very fine. You need to have a very good microscope to see. But when you do this kind of filtering processes, you can see it very easily.
Exactly. So for those of the documents that you get from the government,
Yeah.
maybe you are not very aware of this, but you can look into that. There is a minor dot matrix pattern that you'll see inside the documents.
Not visible from Nikela, but yeah.
Yeah. So which is the same concept, right? So we are translating the knowledge that we have in the physical world into this world. And here we see that if the image has been captured in natural light under the physical conditions with the illumination changes, with the weather changes and so on, that image will look very different compared to image that we have generated, right? So the idea here is to go and find this signature. I'll talk about this in also in the other context. So, but here you can see that now, as soon as I have this background information, the photo response non-uniformity, we call it non-uniformity because if you take a sensor that is, let's assume 3 by 3 sensor, then the signature here will be very different for each camera, right? So this is nothing but some noisy pixels that will be available on each camera, right? So now what we are trying to do is that we are trying to model that one. And yesterday we spoke about GAN, right? And we said that GAN is extremely good at creating synthetic images. Now, how do we detect that if it is generated by a GAN image, by a GAN network? Everybody has done Fourier transform. We have learned this as a signal processing in the signal processing course. Now take the image, just take a Fourier transform of that one. So if you take a Fourier transform of that one, then you start seeing the spread of the signal, which is very different for real images versus the synthetic images. In the real images, you have the frequency that is kind of spread, which is very uniform, which looks natural, as compared to the ones that are generated by the GAN networks, which are very condensed and very concentrated. Right? So now this idea should also give you some directions for the new work, right? So the next time you're trying to create a GAN model, you can also think about, okay, how can I make use of this frequency information to improve the content, the generation part itself. So it's an inverse cycle, right? So you can use it for detecting them. At the same time, you can use this back into the network to improve the quality. Let's take a bit more deeper look into this one. So now I told you about this Fourier transform in this case, right? So let's take another family of transforms, which is called as discrete Fourier transform. And if I do the discrete Fourier transform, then from the original image, I take the DFT, then I can get two different components. One is the frequency component, which is which is magnitude, and then you have phase component, right? So it's nothing but breaking of signal into two parts. As soon as the breaking of the two signal parts, then I can start looking into that and then start identifying what is that it's changing. So look at this particular part. So if you just take an average of all the signals that you capture in the 2D spectrum, then you can average it out and you get a 1D signal, and this 1D signal will be different for real image versus synthetic image. In this case, in this work. This is not our work, by the way. It's the work from this group. So, but the phase does not give you very discriminating information. So that's why they go for magnitude. Okay, so what I'm trying to say is that all the synthetic content that we're creating will leave some kind of fingerprints behind, which can be used to detect them. So we saw the first family, which was based on feature extraction, color, physical appearances, and now we started looking at the fingerprinting here. Let's take a step ahead and then try to look at CNN-based approaches, right? Because we spoke about CNNs in the first lecture. We said, okay, that's our starting point. How can we now use this one for detecting the synthetic content? So here, if you look, exactly the same approach. Nothing is being changed except that the FC layer will be two layered now. So two neurons. One is real image, the other one is synthetic image. Right? And then of course, within the synthetic image, you can have a specified network. From the FC layer, you say 1, 2, this is real, and then this is synthetic. And then within the synthetic, you can also have subclasses. It says it is GAN-based, diffusion-based, BAE-based, and so on. Right? So you can have fine grain. So in which case you can have the second level of classification here, or straight away do this classification by then it has a multi-class setting. Okay, one example of that one. Again, the combination of multiple things, right? So you can straight away use the CNNs, or if it is a video, you can start with the input video, and then you can stack them up as feature vectors, just concatenate all of them together. And then once I have that, I can learn the LSTM, And then from LSTM, we know that LSTM is nothing but sequential. So the previous frame has a relation to the next frame. The next frame has a relationship to the upcoming frame. So I can use this logic to detect the deepfakes. If there is any inconsistency, the signals between two frames will be very different, right? So I can use that idea of use that idea for detecting the deepfakes.
So if we are doing this first LSTM, then why we have to stack them with one after another? Instead, we can just pass them through one after another and then.
Sure. What they are trying to do is that they are trying to collect 20 frames together, and based on 20 frames, they are making a decision.
Then in next cycle again 20.
20 frames, yes. Every first frame 1 to 20, second frame 2 to 21, third frame 3 to 22, and so on. So they are collectively making that. And
Number of computations will be.
or the decision will become much better, right? So if I'm making a decision on 2 frames, it's very difficult, or let's say if the accuracy is 80%, with 20 frames I can have improved accuracy, right? So that is what you are also seeing in this case, right? So the accuracy kind of changes between different configurations. So with 20 frames you see at 99.5, but with the 80 frames you see around 99.7 here, right? Uh, so maybe this is the wrong column to look at. This is the right column to look at. You see that 96.7 and it increases to 97.1. Okay, and then there is this other network which is called as Mesonet. Everything is very common, right? So you have seen all of these components in the last couple of days. You have seen convolution layers. You have seen normalization, max pooling, and so on. You stack all of them together, and this network has been used. And in this case, they show that whenever it's a deepfake, these are the areas that are getting activated, and whenever it's real images, these are the areas that are getting activated. So in this case, there is really nothing engineered. It's left to the network to learn the patterns. Okay. And then we also spoke a bit about the videos. As soon as I have the videos, going back to the idea that you have, right? I can take every single frame, and then I can have a channel for that. So if I have 20 frames, I can pass each of those frames into the network and extract them together. And then instead of LSTM, I can put an RNN, right? So now RNN is a bit more sophisticated than LSTM, but then it will give you better results. Okay. So with the recurrent strategy, this is how it would look like. Just forget about all the math that is behind, all the area that is there. But now you get a new addition, which is nothing but bidirectional, right? So I can make the decision on this frame based on the 2 other frames, and also the 2 frames before that, right? And then I can go to the next frame. I could do the same thing, backwards and forward. Okay, and then again, now that I have a number of frames, there is no reason that I cannot exploit all the frames to detect the synthetic content, right? So I can use that when using different architectures. In one of the architecture, the identity features has been used from ArcFace here. They extract the features, and then from each of the frame, they stack all of them together, and then they assign the weights for each of the different frames. Which is nothing but, let's say if we have 10 experts sitting here, then I know that Professor Nain is very good at detecting the synthetic content. So I tell her she gets a weight of 0.5, and rest of the 9 people, we divide the weights among ourselves. We say all of our votes count to 0.1 or 0.05, but her weight counts 0.5, right? So now I can have this weighted strategy to improve the performance, which is going to give you better results. Okay. And then today we spoke about the attention mechanism. So if I can use the attention mechanism to create the synthetic content, why can't I use the same logic to detect the content? So then there was this work in 2021, which is based on multi-attentional deepfake detection, where they take the frames as shown here, and then it's passed through a number of backbone layers, which is going all the way down here in this part. Maybe I should just mark it all the way here. this area, and then at every single point they are taking the features away, and then they are doing some processing here where they call it as texture enhancement block, and then they compute the features back again. Now that I have two different layers, one layer which is dealing with the feature extraction, the other layer I can use it as attention module, right? And again, depending on the strategy that you're using, you could also plug this one in up here maybe, right? I don't recall it properly right now. Maybe if you read into the paper, they have tried to fix that attention model in different places. But the idea here is that everything that we discussed in the morning can now be used, right? The attention, the idea of the attention. The nice thing about this work was that it was also able to localize where exactly has the manipulation appeared. For instance, if you look very closely into this, so this one is face to face. So this is the original frame, this one. So this one is the original frame, and this is the face to face, where they're just taking one face and then trying to change some parts of the face, one of the approaches, and then it's able to localize them very clearly, right? So now why does this become very important? If you're a police officer and then you look into the image and you say that I can't accept this image because it looks like it's edited. Now you have to explain this to the person who's submitting this, right? He might argue that, well, it's not edited, but then if you have tools like this, you can show and pinpoint, look at this area, this is the area that has been manipulated. Okay, so the attention mechanism that we introduced can also play a significant role in explaining the decision making process. Good. And then now there was another work in 2019 which was again based on the idea of using multiple frames, but then putting all the information together so that you can treat it as a volume, which they call it as capsule, and then based on the capsule, then they can make a decision, right? So this work was also very well received, and here you see that if you have a capsule of certain activation, for instance, this one, again this one, you see that this can be, this is a real image and this is a fake image. And this is purely defined by this activation, right? You have an activation 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, almost 12 blocks which are highly green, which indicates that this is a fake image. Okay, and then now while we are talking all about these deep learning based systems and the inversion of GAN based approaches and so on, there are also really simple and trivial examples where you can detect so many things in a nice way. If you look at this one, right? If I have a number of frames, and for each frame, take a particular pixel, take one area, and then traverse in the volume, right? So it's nothing but you have a frame, 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 frame. So take one particular point here, and then go all the way inside the network, also all the way inside the video, and then start putting them here, right? So this is nothing but RGB value. It's nothing but the pixel value. It has three particular values, right? So if I stack all of them here, if it is a real video, the skin color will not change from, let's say, 255 to suddenly to 100. It will be lying in a similar range, right? So that is an indication of whether the content has been generated automatically or if it's a real content. And the second aspect here, if you look very closely, they are all looking at the skin area, right? So they are taking the areas which correspond to the skin. And if you look at the skin, it is nothing but the same area that we use for PPG estimation, polyplethysmography estimation. So those of you who have gone to the doctors, they put a simple device to measure if the pulses are proper, if they are normal, and this is an indication of that, right? So for that signal, the R signal will follow a particular trend, the G signal will follow a particular trend, and the B signal will follow a particular trend. So your red channel, blue channel, and green channel. So if they are not manipulated, if they're not synthetically generated, then the variations would be very normal. Right? So in the case of synthetic generation, probably they would vary very much up and down. Okay, so as soon as you have this one, so then you could also plug in the different models, right? You can say that, okay, any person that is appearing in a particular frame will appear in a certain way, and the way the person moves within the frame will be in a certain way. So the random videos will not, no, the real videos will not go from left to right very instantly. There is a transition from going from left to right. All the frames are captured in between. But the synthetically created content, there might be some frames where it will be skipped. So those are the frames that you are interested in capturing. Okay, and then again in 2020 there was another work that was published here. Here the idea is that you have a physiological signal which you are trying to estimate from the face purely based on the skin color. You look at the RGB, and every time there is a change, then the values would drop, and they would drop in a certain fashion. So here, if you look at the what they're trying to basically do is they're trying to estimate the heart rate. So for a natural person, the heart rate will follow a certain trend, and if it is synthetically generated content, the trends would be very, very different. They would not follow the natural physical laws. And then, okay, now we can argue that, okay, what happens if I'm wearing makeup? What happens if I'm wearing mask? Right? These are common problems, right? So then what you can do is you can, instead of looking at the whole face image, you can chunk it into small parts. You can say, okay, now I take only the region above the nose. Now I take only the region above the chin, the forehead, and so on. As soon as I have this one, so I have multiple systems that I can combine. So this is nothing but like expert system combination, right? So I have multiple A, B, C, D, E systems. All of them will give some decision. Now, as soon as I have the decision from them, I can start making a decision out of that, the combined decision out of all of them. So the patch-based approach is something also very, very popular. By the way, is there anybody who can recognize this fake image? Who this person is? That one is Amy Adams, but second one? You have some guesses there?
Emily Blunt and Emily.
Is it not Nicolas Cage?
Oh my God. Really?
You see that now, right?
Yeah, he is superimposed. That is so bad.
Okay, and then there is also this other laws, right? There are certain physical laws that we always follow. If I'm in a particular volume, my head will be always in this particular volume, right? My head can't go from here suddenly all the way to here without some transitions. And then there is this approach which was published in 2021, I think. This work was taking care of this particular aspect. We see some particular phenomena in the natural way the person moves. And if I can capture it in a 3D volume, then the face landmarks, whatever we spoke about, they're supposed to be in that volume itself. They can't abruptly transit from one volume to the second volume. Now, as soon as you have this one, so then you can create a method which says that, okay, all the normal transitions will be real class, all the abrupt transitions will be in fake class. And this is also quite evident in this case, right? So let's zoom into this one. You see the ghost artifact that is coming here. So there is one here and there is one face here, which means that you are now suddenly getting two set of landmarks, which is nearly impossible when the person is one person. Okay? So this intermediate transition can give you an idea of whether the image has been manipulated, whether the video has been manipulated or not. Okay, what is also interesting here, the part that we should appreciate is that unlike most of the other works who were talking only about detecting same kind of images, where the training set was similar to testing set, this work moved one step ahead and they started looking at generalization. So which means if the images were generated using GAN, can we detect if you have trained it on diffusion models or vice versa? If I have trained all the detectors on diffusion images, can I detect the images based on GAN? Okay, so that was again based on the video accuracy. And then there is also a plethora of approaches which are based on this old style, old school machine learning computer vision, where they're looking at the features such as Hawk features, BSI features, LBP features, and then you're constructing a simple SVM classifier. Okay, and then I'll talk a bit about this last part which we mentioned, right? So every time I'm doing something, today I know there is VAE, diffusion, and then there is transformer, there is GAN, which helps us to create the content. And what I'm not guaranteed is tomorrow there might be a new technique. So every time I'm going to create a detector, I should also take care of tomorrow's need as well. So this means that the unseen data should be detectable. So if tomorrow one of you come up with a very wonderful technique which can create highly synthetic images, highly realistic synthetic images, it should still be detectable in a generalizable setting. That's what we call as generalizable setting, right? So in the earlier works, we have already showed that the accuracy when it is known setting is very high. So the error rate in this case, you see that it's only 3% error, 4% error, less than 1% error, and so on. But the moment you make this combination, train on one particular kind of data, test on different kind of data, then it starts failing. Now you can extrapolate the same problem to another medical domain, right? So suppose you are detecting all the images which are manipulated based on Philips machines, and then if you are trying to use the same method for machines developed by Siemens, then they might start failing. So what we want is that this device independent, data independent, agnostic methods. So in the very early work, we showed that it's not possible to generalize them, or the methods that were available at that point of time, they did not generalize. And then we started looking around this area. So one of the idea in this case is to look at supervised learning, supervised contrastive learning. So the idea is quite simple. When I'm taking some image and if I'm doing a transformation of that images, if it is real image, the transformations will be similar or they will have similar kind of characteristics compared to the fake images, right? So I have the channel for one set where I'm transposing the image to A and B, in this case here. So this image I'm augmenting to A and B, and then I'm trying to learn an encoder, again the same things that we have been discussing in the morning. And then there is a latent vector which is representation here, and then I can put into a projection head which is another set of layers. That could be any of your favorite layers. And then once I have this, the latent space between two images, which is zx, z1 and zi and zj, should be close enough. If they are not close enough, that means that they are manipulated in some way. So now you see the whole connection, right? So everything that we have been discussing so far is also used for improving the systems by just saying that all the distribution space should lie in the same area. So the points in the distribution should lie in the same area, or at least close enough. Now you can understand the concepts of mu and sigma that we were talking about in the latent space. So the distribution should be very compact and very dense. If it is not dense, that means that they are coming from a different distribution. Again, I'll not get into the math part of that, but then you can look at some common terms that we were discussing. We were discussing about this maximizing something and minimizing something. So what we want to maximize is we want to maximize the similarity between the latent space of same image, which is not manipulated, while maximizing the difference, no, minimizing the similarity between the representations which are coming from real and fake. Okay, fake in the sense that it can be any synthetic content. Okay, I'll not spend more time on this, but just you get the idea that we can use the concepts of similarity. You can use the concepts of latent space to create this method, and in this case we see that it's a very simple method. And then once I have the latent space, and this is some classifier, some random SVM based classifier which we can train, or a deep CNN based classifier that I can train, and then I can have better results there. And then, as I told you already before, it's not just us who are looking at this generalization problem, right? So there were two other works which were looking at this. One of the work was that I showed you earlier, which is based on this bounding box volume. And the second work is also a very nice work, which is purely based on probability distribution. So here in this figures, you can see that, if I can zoom that in a bit. So in this case, you can see that they're saying there are two different domains. There is a source domain, there is a target domain. The source domain is nothing but your real images. The target domain is nothing but your generated content. So if I model that, now any encoder, any of your favorite CNN, extract the features, and there is this latent space. And if they're all coming from the same distribution, if they're all coming from the real distribution, they will lie in one area compared to the images that are coming from synthetic content. Now, if you go a bit deeper into this direction, you could also be designing this encoder in such a way that you can have multiple clusters for different techniques. One cluster for GAN, one cluster for VAE, one cluster for diffusion, one for real images. Right? As soon as I have that, then the idea comes down to the whole approach comes down to separating them. So which I can do in this space. Right? So I can simply learn a boundary, then I can simply plot a boundary here, which I was showing in the linear representation yesterday, or sorry, linear regressions on Monday. So where we were having some points and then trying to separate them using a boundary. Okay, I think we can take a break in few minutes, but just let me continue with a couple of more things. So and then as we already have the luxury of having multiple frames, what I can do is I can also combine all the frames together, right? So here you can see that by combining different independent decisions, you can improve the performance. And also at the same time, by doing the supervised contrastive learning, it inherently improves the explainability. It doesn't solve the problem again, but it improves compared to the existing methods. For instance, if you look very closely into this image here, so you can see that the highlight is in this area, while in this case, the highlight is actually moved back to the face area, right? So it gives an idea that how each of these methods contribute to better explainability. Okay, this I'll not spend time on, but another approach. Now I gave you a motivation of generalization, but then I also gave you the motivation for using the color space. Now what you can do is you can combine the ideas of color space together in a network where I'm looking at pairwise interaction. So if I have a real image and a deepfake image, what I can see is that how much does the color change in both of these images across one channel RGB or across multiple channels. For instance here, right, you have RGB and then I can add it with HSV, I can add with YCBCR and so on. And then by learning the interaction between these two, I can say that, okay, within the same image, the latent space will be closer, irrespective of what color space I'm using, than the other image. The other image in our context is the image that is synthetically created, right? So now look back again here. So if you look very closely here, now we are back to the same problem, right? So latent space, as soon as I have the latent space, the embeddings, then all I need to do is minimize, maximize. So minimize the similarity, maximize the similarity here, minimize the similarity between these two, right? So again, so once you have the concepts in place, you can just simply plug and play. Okay, this is nothing but the network architecture, but you get the idea that you can use such information for going for looking at color, looking at video and frames all put together, you can create better systems. And then there's also, if you look into the paper, we also report different results where we show that different combination give different results, which means if you are a company, you can combine all of them together and then provide a better system. In the case of research, we only show what is performing good, what is not performing good, but as a company, you can combine all of the systems together. Okay, and then what does it also lead us to? It also leads us to better explanation. In this case, if you look at the embedding space, the embedding space for each of them are very distinct. Now you see that the real images are here, all the real images, while you have face-to-face here, neural transfer here, diffusion here, sorry, deepfakes here, face swap here. So the idea is to create such systems which can separate these distributions, right? So these clusters of points. So this is another point that I'll come back to in the lecture in the topic on explainability. But again, the idea here is to show that compared to the existing methods, this approach was slightly better, but still not solving the problem. Why it does not solve the problem, I'll discuss in the next slide, in the next lecture. Okay, should we take a break here and start the next session? Yeah. Okay, so we can take a break here, and then I have two more small concepts to explain, and then we can go on to the applications of GAN networks.
Take a 5 minute break. You can go take a deep breath, have some water.